A very good evening to all of you and welcome to today's session. So today we'll be talking about regularization. So just give me a minute and I'll just share my slides and we'll start. Just a second. Okay. So I think my screen must be visible.
Yes, ma'am.
Yeah. Okay. Thank you.
Good evening, ma'am.
Good evening. Good evening, everyone. So today we'll be discussing this topic, regularization, in which in specific we'll be talking about L1 and L2 regularization, which is also called Lasso and regression, respectively. So to start with regularization, first of all, just a quick recap of about bias and variance. Though we have discussed this earlier. So bias means that whenever we are making a model fit on real world data, say training data, then what could happen is that, sometimes the model could be so generic in order to avoid it being very complicated. It could be so generic that it is not able to learn the patterns in the data and it is actually underfitting. So the situation of underfitting is also said to be bias. And we don't want such a situation where our model is so generic that it is not able to learn the patterns in the data and therefore performs poorly. Then we have something called bias. What does bias mean? Bias means that, variance. So variance means that uh, the difference between the predicted values and the actual values is very low, and in that attempt overfitting has been done on the model. So we also don't want that, because then the model becomes very specific to the given data, and therefore what we want is a bias and variance trade-off, where both bias, we don't want bias, we don't want variance, but we want both of them to be optimally low, because both of them cannot be at the lowest at the same time. So we want them to be optimally low. So we want to choose a point where we develop our model in such a way that bias and variance get a trade-off. So if you see from the graph here, so if you see here, what you can observe is that initially when the learning is not done, what happens? So we are having two kinds of errors being shown here. The bias is shown in this blue dotted line, and we have the variance shown in the green dotted line. So initially, when the model has not learned much, and it has actually not been able to learn the patterns in the data, the error, so this is actually nothing but error or loss. So this is high. So error is high at this point. As the model keeps learning the data, the error starts becoming lower and lower. So this is the bias term. Then if we talk about variance, then what happens is initially the variance is very low because the model has actually uh, tuned itself too much or overly over the training data. So this value is very low. And as the model keeps getting generalized, this becomes higher and higher. So therefore, when this is high, that is when bias is high, variance is low. When variance is high, bias is low. And both cannot be high at the same time. So we want to have a point which optimally minimizes these two, and this will be that point. You can see here. Both of them are optimally low. We don't want underfitting, we don't want overfitting, we don't want any of these. So this is called the bias variance trade-off, and it can be explained with the help of this graph that you are seeing here. Okay, now let's come to our today's topic. So having said that we don't want bias, we don't want variance. So then this means we don't want underfitting and overfitting. So then how to prevent overfitting and to some extent underfitting? So regularization is a very, very important and a very popular term that is used in context to model that wants to prevent overfitting. So how it does so? So overfitting is prevented by the help of, so in case of overfitting, the model will be overly tuned on the training data, and therefore when unseen data is presented to the model, its performance will degrade. So what regularization will do is that it's going to penalize a model that is very complex. Overly complex models will be penalized, and regularization encourages simpler models that have a higher generalizability, and therefore in this way overfitting is actually prevented. And to do this, the loss function that we have studied earlier, that is the sum of squared error, also includes certain other parameters that help to penalize these overfitted values or parameters. So we are going to discuss this. Just a second. Okay. So you can see here, let's say that we have to predict a person's height. Okay. So to predict a person's height is the given problem. The attributes that are given to us are like weight, salary, ethnicity, eyesight, and all. So if we have to predict the height, then it is very clear that the weight may play a role, ethnicity may play a role, but salary may not play a role, eyesight may not play a role. However, if all these attributes are given as input to a regression model, then it's going to assign some weights to each of these values, okay, each of these attributes. And then what it's going to do is, in order like this, it's going to build the model in such a way that whatever best estimate of the height it can get, it gets. So in this process, what it does is it just tries to overfit. So there are attributes that are useless to the given problem, but it will unnecessarily try to fit the model, the regression model, using all these attributes just because they were given to it, and it has no way to discriminate what to do with that, and so it uses them and the model becomes overfitted. This is what you're seeing in the lower part of the slide is just an example of overfitting and underfitting. So red dots indicate the points, the data points, and here what you are seeing is a overfitted line which is trying to pass through each and every point. So this is nothing but an example of overfitting, and this is what happens in overfitting. If we talk about underfitting, there's a very generic curve that fits all the points, and the fitting is not very good because the error with respect to most of these points is going to be high, and therefore the total error is going to be high. And then the right fit is the one that optimizes, and it tries to reduce the error to some extent. So here what we want to do by regularization is to do the right fit and avoid overfitting and underfitting, primarily overfitting. So now, so in regularization, we try to, assign penalty. Now, what happens is that it is true that sometimes not all the predictors are useful to the given problem. And if we, try to fit a function, what the linear regression will do, regression will try to minimize the loss function, which is nothing but the sum of squared errors, as we have discussed. And therefore, it will just try to fit something. So in regularization, as I said, that we will try to counter this problem by adding a penalty term. This penalty term will help to downgrade or to weaken some of the predictors that are irrelevant to the problem. So first of all, we are going to talk about Lasso or L1 regularization. It's also called L1 penalized regression. So Lasso is actually an acronym that stands for least absolute shrinkage and selection operator. So I am going to tell you the meaning of each and every of these as we go along. Right now, you can just remember that it is least absolute shrinkage and selection operator. So this method, Lasso, is very popular, and it helps us to select and estimate the coefficients when we talk about linear regression model. Remember, we are talking about linear regression models only, and it is going to uh, prevent overfitting by assigning some of the coefficients in a linear regression equation to 0. Remember, what is a linear regression equation? It could be something like alpha plus x times beta, beta naught plus x times beta 1 plus, uh, you know, uh, y times beta 2, like that. So if some of the coefficients are made 0, then the model overfitting can be prevented. So how this all happens, we are going to study today. So first of all, before going into what is this all about, let's look at the different terms that make up the acronym Lasso. So Lasso, the term least. The term least refers to the least squares method, because we are talking about the sum of squared error and it is based on least square. Therefore, the term least has been used here. Then absolute means that in this particular case, when we talk about Lasso, we are going to talk about the absolute shrinkage and error. Shrinkage will be reducing the coefficients in such a way that they are reduced and the penalty is minimized. And then selection operator refers to the fact that Lasso helps to select certain features from the model. So these will become more clear as we go along. Okay, so I'll just request you to bear with me for some time, and then you'll be able to see more of these things. So now let's assume we have got a data set this data set has got capital N number of observations. Okay, so these are the number of observations. And each observation is made up of P attributes, right? So if we are talking about the ith observation, then it will have attributes xi1, xi2, xi3 till xip, where P is a total number of attributes or independent variables that are there or features that are there. And the predicted variable is y. And its ith value is said to be yi. Okay. So now before we go into this, let me just give you a recap. So if you all remember that if we talk about linear regression, which we studied earlier. So in linear regression, we have something like, just a second. We have this y is equal to alpha plus beta times of x, where y is the dependent variable, x is the predictor, right? So since this is the predicted value, and we know that there will be always a difference between the actual value and predicted value. Therefore, this difference will be accommodated in this equation by where this epsilon is nothing but some error that is introduced here. That stands for the difference between the actual value and the predicted value. This much is the predicted value. This is the error. This together will give us the actual value. So if this is predicted value, then this is the actual value. Okay. Now we are given x. So we are having a set of n observations. So this means x, which is the input, is a set having x1, x2, x3 till xn values, right? And each of these is having p number of attributes. So therefore, this x1 will be like x11, x12 till x1p. And then x2 will be like x21, x22, x2p. And then this will be like xn1, xn2 till xnp, like this. And then this can actually be represented just allow. So if you think of it, the data actually could be represented in a n cross p kind of a matrix. If you remember, I told you about it earlier also, where you have like your observation 1, observation 2 till observation n. And then you have your attributes like P1, P2, P3 till PP. And in it, you will have values like x11, x12 till x1n, like this, xn1, xn2, xnp. Sorry, this will be p. Okay, and this stands for x1, this stands for x2, this stands for xn. Okay, is it clear up to this point? Any questions, anyone so far?
Clear, ma'am. Clear.
Okay, good. Meghna, you have a question?
Ma'am, can you please come once again on that P part, like how this x1 to xn, are you converting to P matrix, I mean n cross P matrix, and why?
Okay, so So I said that the set of inputs, this is the inputs, right? So there are a capital N number of inputs given by x1, x2, x3 till xn. Okay. Now each of the input is having a p number of attributes. So each is having p features. For example, I can give you a set of people. So this can be similar to n persons data. For each person, we have height, weight, age, date of birth, etc. Okay, so each of these person is nothing but your x1 or xi, and this height, weight, and all are x11, x12 till x1p. Similarly, for the next person, it will be this is x1. For next person, again, these will have different values. So, like this, you get the input. Each input has, just a second. Give me a second, please.
I think I'm clear, ma'am. Sorry.
Okay.
Yeah.
Okay. Allow me a minute to adjust my battery. Just a second. Start. Okay. So now you have all these observations, and then I already talked about this expression. So I already talked about this expression, right? So now let's put this for any particular, value. So here, just a second. So for yi, again, I'm facing some issue. Give me a second, please. Give me a second. Just allow me a second. So I'm facing some technical issue. Please allow me 2 minutes. I'll resolve it and then restart. Yeah, sorry for that. Okay. So, then we have this expression which I already gave you, which is y is equal to alpha plus beta times x plus error. That was a generic expression. Now, if we suppose want to talk about the ith value, then yi will be equal to alpha plus, uh, just a second, just one second. Okay. So this will be alpha plus why this is because in this case we are having x having p number of attributes. So j will take up value 1 to p. I can also write it more clearly. Yi is equal to alpha plus j is equal to 1 to p beta j xij plus epsilon I, like this. Its full form could be, if I want to, let's say, choose yi, I could write it as yi equal to alpha plus beta 1 times xi1 plus beta 2 times xi2 plus so and so forth, beta uh, k p times xip plus epsilon I. So this is a short form of this whole part. Okay. Now, if we have to find out the error in the prediction, then this epsilon I will be equal to yi minus alpha. I'm taking this part here, minus summation of j is equal to 1 to p, this is p, beta j xij. And since we have the error as the sum of squared error, we have sum of squares of error. They are also called residual sum of squares. It's the same thing. So, therefore, this square will be equal to the square of this whole term, j beta j xij whole square. This is what our error will be. And if we have to find out the total error, that is, this was the error on the ith term, right? If we have to find out the total error, then we have to do this for all the observation. This was only for the ith observation. So that will be how much? That will be this whole thing summed over all n observations. This is the total error. Okay. So now we have found out this is the total error, and we want to minimize the overfitting. So to minimize overfitting, remember that whenever the least square works, what it does, or the linear regression works, what it does is that it's going to assign some values for each of these coefficients, right? These coefficients that we discussed. And these coefficients are the ones that are responsible for doing overfitting. Now, if we have some mechanism to put a cap on these values of the coefficients, then in that case, we can control these values to some extent, right? So then we are going to do this next. So in Lasso, what we are going to do is to avoid overfitting. Threshold T is chosen. It's a value, positive value. And it is chosen in such a way that the sum of all Bj is going to be less than or equal to T. So, or in other words, we have beta 1 plus beta 2 plus beta 3 till beta p. This all will be less than or equal to T. Or we can say that j is equal to 1 to p. Beta p is going to be less than or equal to T. So this is also called a tuning parameter because it helps us to fine tune this particular model, and it is only applicable to the coefficients in linear regression. Okay. So like this, we can actually penalize the coefficients uh, by putting a cap on them. Now, how are we going to put a cap on them? We'll just see. Okay. So this I've already told you. So I'll just skip this. So everybody clear about how to find out the error? I've already told you this expression, how it comes, and all these things I already explained to you. If you have any questions, please let me know before I proceed.
Ma'am, this is so this error that we just talked about, it is just the difference between actual point and the one that we have calculated, right?
Correct, correct, correct.
I mean,
So
okay.
yeah, so this is the actual value. Predicted was hat equal to, if we call this as a sorry, as alpha plus beta x, right? But there is a difference between predicted and actual value. So this actual value is the predicted value plus error term. So we are calculating the error here and then squaring it to find out the loss, and then this is the total loss. It's okay.
Okay.
Okay. So now what we are doing is that we want to avoid having overfitting, and we want the regression to become more simpler. However, as we know that in the basic form, the linear regression is going to overfit because of a large number of uh, coefficients that it is having. So we want to control the coefficients in some way, okay? And therefore, we are going to define a threshold t, which is a positive number or a positive integer, in such a way that the sum of the magnitudes of each and every coefficient put together will always be less than or equal to t. And this is called the constraint on the values of beta. Okay. And the lesser this value will be, the more will be the shrinkage. I'll explain to you what shrinkage means slightly later. So as of now, you can just uh, remember that smaller the value, the more will be the shrinkage. And so this is a tuning parameter or a hyperparameter that needs to be tuned so that we have the correct balance between underfitting and overfitting. So now let's assume that there is a case where, we are, let's say we are having an example in which we are having only two coefficients. Okay. So we are having a predictor where we are having alpha plus beta. So these are beta 1 and beta 2. So beta 1 times x1 plus beta 2 times x2, something like that we are having. And let's assume that when we apply linear regression to it, simple linear regression, it's also called ordinary least square, then the solution is somewhere here. because the values of the coefficients, let's assume the values of both the coefficients come out to be 10, and so this is plotted here. Okay. Now, as we know, we discussed that in Lasso, we are going to apply a threshold value on the summation of the magnitudes of the coefficients. For example, if we say that we assume t is equal to 4, then the summation of beta 1 magnitude plus beta 2 magnitude has to be less than or equal to 4, right? So this means that we can have a set of values for beta 1 and beta 2. For example, one combination could be beta 1 is 2, beta 2 is also 2, and so their sum is less than or equal to 4. And if plotted on this curve, this comes out to be here, the green point. We are also allowed, because as I said, beta 1 plus magnitude of beta 2 has to be less than or equal to 4. We could as well have this as 0 or this as 0. So this means that we could have different combinations out here, like beta 1 is equal to 0 and beta 2 is equal to 4, or beta 1 is equal to 1 and beta 2 is equal to 3, beta 2 is equal to 2 and beta 2 is equal to 2, sorry, beta 1. And then beta 1 is equal to 3 and beta 2 is equal to 1. And beta 1 equal to 4 and beta 2 equal to 0. And then there could be combinations like this is 0, 4. Then there could be combination like 0 minus 4. Then there could be combinations here also like minus 1, 3, 1 minus 3, minus 1 minus 3. Because remember, we are talking about magnitude only. So in magnitude, the sign doesn't matter. Similarly, it could be minus 2 or minus 2 and 2, or it could be 2 and minus 2. Similarly, this could be 3 and minus 1, or minus 3 minus 1, or minus 3 and 1. And then this could be minus 4 and 0 also. Now suppose we plot this. And let's say that so then if we try to plot these, what we will get here, this is of course 0 values for the coefficients. So the one point will be 0, 4, beta 1 0 and beta 2 4. Here, another point will be here, another point will be at 1 and 3. So here, then at 2 and 2, which will be here, and then 3 and 1, like this. And there will be other points like 0 minus 4. So this is 0 and this is like minus 4. And then there will be point like 1 and minus 3 here, 1 and minus 3. So it will be here like this. So what we will get is a shape of this kind, right? And remember at 10 cross 10 was our original solution, which was using the least square method, least square estimate, or the OLS, ordinary least square method. So now what we want to do is, and of course another thing is that this is the case when the value of t is equal to 4. If t had another value, let's say t is equal to 8. If t is equal to 8, then these values will accordingly change. For example, this will become 8 and so on and so forth. So we can have something like a rhombus, which is a double heighted rhombus. So if this was, so it will be something like this. Okay. So in this case, the constraint is 8. So we are expanding our constraint, okay, like this. And now if we actually, okay, now if we look at the distance, so what are we trying to do here? We are trying to actually add a, no, we want to, control these coefficients. In a way, what we want to do is, okay, I'll proceed and then come back to this slightly later. Okay, so this was the initial one that I had shown you. Uh, so this was a calculation when we had this value. This was the original one. This is at 2,2. And this is the diamond that you get with a constraint of 4. Now, in Lasso, what we try to do is we try to find out, we try to minimize the error. So the objective here is, if you, okay, yeah. So this is the point where the value of the coefficients is 0. Remember this equation I told you, y is equal to alpha plus beta 1 x 1 plus beta 2 x2, something like that, right? So this is the point where the value of beta 1 and beta 2 is 0 and y becomes equal to alpha. This is that point. Or this is a point where the constraint is very high. Okay. So it is at this point, it is the model, if we are talking about putting constraints where the value of beta 1 plus magnitude of beta 2 must be less than or equal to t. In this particular case, t is 0. Therefore, this is forced to be 0, this is forced to be 0. Obviously, when we force these two to be 0, then both of these features will be gone from our equation, and what we'll have is y is equal to some alpha, which is a constant value. So we don't want to be so much restrictive also. As we increase the value, this value, what happens is that we are allowing some values, some positive non-zero values for beta 1 and beta 2, or at least one of these. Now, this is the value that is obtained using the normal method of regression. So this is the value which is the best fit model, or in other words, this is the model that has been actually fitted in the normal way, the normal fitted regression model, and it might be overfitted also, like it is having least error, right? Because it's having least error, that's why it's overfitted on the training data. And this is the one where the coefficients are 0. Or in other words, this is a constraint that we are putting, and this constraint is forming a diamond kind of a thing. So what we want is we want to bring these 2 points closer. By doing an optimization, we want that we don't want the coefficients to be 0, because if we have coefficient 0, sorry, just a second. So if we have all the coefficients 0, then we are left with no, predictor being used in the prediction. So we don't want this. We also don't want this because this is leading to overfitting, because we are unnecessarily utilizing all the coefficients or giving them high weightage, and the model is becoming overfitted. We want to bring both of these close together so that this overfitted, error in this becomes lesser. So to reduce this, what we want to do is to bring it closer. We want to, find out the distance between these, and wherever the distance gets, minimized, that is what we are looking for. So suppose we draw a perpendicular line what happens is the point here is 2 cross 2, but if we look at it, the distance, so if we try to bring these two, what will happen is that, uh, so the distance here is equal to, this is a 2 cross 2 point, this is 0, this is uh, 0 cross 2. So the distance, this distance actually will be square root of 2 square plus 2 square. And this 2 square plus 2 square will be how much? It is approximately 2.7. So this distance is 2.7. However, if we look at this vertex, any of the vertices for that matter, this distance is 4, right? So this means that, if we try to reduce the error, the mean square error, which is the error of this point, and we choose this particular point, we are reducing it by 2.7 only. But if we choose this particular point, then we are reducing the error by 4. So therefore, the solution will always proceed like this. It will rest at this point and not at any other points. So in Lasso, what happens is that the solution always looks for a minimum, and this minimum always goes to the vertices, because the vertices give a distance of 4, and therefore the distance of this point, if we call it some point, let's say the ordinary least square maximal point, so the distance between this and this is minimized, whereas the distance at any other point will be more. And this distance is indicating the amount of minimization we are doing by, so what is happening here? We are having this penalty, right? So our coefficients are not 0, but they are some positive number, and we are going to, control them. So if we control them at this point, then what will happen? It will happen that the constraint will be satisfied in the best way, and at the same time, overfitting will reduce, because the error would have reduced to a maximal amount. So you will know more about it as we go along. I will just show you. Just allow me. So this is the same thing that I explained to you. So it means that it's always beneficial to select the vertex because of the diamond, because it sticks out or it extends more away from the origin, and therefore it helps us to reduce the error in the best possible way, right? And therefore we will always choose this. Now, what I want to show you is why I was talking about this is, remember what is our, error function that we just discussed. Our error function consists of two terms, right? If you remember, and what are those two terms? Those two terms are uh, the square of the errors that we discussed. Like for example, if we talk about the total error, this is what? Right? This was the error, plus we have added the sum of all these betas, and this should be less than or equal to some particular value, right? So this is what is our error all about. Okay. So here, this particular term, this we are saying that it will always be less than or equal to some value t or s or anything. You can call this t. And this particular term here is expressed by this diamond out here, or the constraint. So this is the cap on the value of coefficients, sum of coefficients, magnitudes of coefficients, whereas this is the error term. If we plot this error term, which is nothing but our loss or mean square error, then it will come out in the shape of ellipsoids or ellipses, which are actually concentric to each other. This will be the value which is the maximal value, and these are the concentric circles which show values of the mean square error at different combinations of betas. Okay, at different combinations of beta, these values will be different, and we want to find out a point where the constraint satisfies the mean square error, and this is the only point where this constraint will satisfy this particular mean square error, and this is a point that we are looking for in our minimization problem here. So that's why I told you that if we take any other point, let's say this point, then it will not satisfy minimum, because this distance is 4 and this distance is much lesser. Therefore, here the amount of minimization between this and this will be more versus this, and this will be less. So this is what we try to do in Lasso. Okay, so now having talked about this, um, any questions so far, anyone, on whatever we have discussed? Yes, Ashish, you have raised a hand.
Ma'am, do we completely remove the variable? The
The
check, or we reduce it to some value? Because
yeah,
this sigma of beta we didn't see in the previous equation that you had explained, where I had asked, is it the difference of the actual versus what we have predicted? But uh, do we actually remove the feature itself, or we reduce the value of coefficient? I mean, I understand by this ellipses that you form, that it is probably the vertex of the diamond.
yes,
Maybe we are
correct.
removing it. So
Yes,
don't we reduce the beta instead of removing it altogether?
yeah. So in case of Lasso, we reduce, we remove some of the variables. And this is a very simple situation where there are two variables only. In a multivariable situation, some variables will be reduced to zero. Or in other words, what are we doing? We are simplifying the given linear, equation or the linear regression model, so that some of the predictors which are irrelevant get removed because they become zero.
And what if we have less information? So it helps when we have so much information. But if we have less information and then we are doing this, it will further eliminate some of them. So is it good for overfitting and underfitting both, or just one of them?
It is good for overfitting. Therefore, if we are having already we are doing an underfit, when then we don't apply Lasso, because we are doing regularization, and
Okay.
regularization means removing overfitting.
Okay.
Okay, and this is the summation that I had shown you earlier. As you were mentioning that this was not there, so I had shown you this. Here also,
Okay.
this is the expression. Plus, we are going to add that summation part. This was the base equation.
But ma'am, in the final equation,
Mm-hmm.
since this summation is just a small thing, right? I mean, the equation can be anything. So beta 1 plus beta 2 plus beta 3, and
Mm-hmm.
so in the formula, does it make any big difference? Because it seems like it's just a summation of all the betas, I mean, the coefficients. Uh, I,
Actually,
mm,
yeah, I got it. Actually, point is not this. Point is that by putting this, we are trying to put a cap on the beta values, isn't it?
mm,
I suppose I have a linear regression equation that is fitted, okay, and it has some beta values. because my model doesn't know what attributes to choose, which it doesn't have to choose. We just gave, and we also didn't take any cognizance of the matter. We just gave some, all the set of attributes, whether relevant or irrelevant. And because the model works like this, it will assign some coefficients and fit all the given attributes in the model, right?
Right,
It
right.
cannot leave out. Now, the thing is that we might know, or it might come to us that some of these are anyway going to be irrelevant. But because we have, the model is built in such a way that whatever attributes you give to it, it's going to model it, and it's going to assign some weights, and we have no control over it. Once we give all these as input to the linear model, it's going to fit it. That's it. And we can't do anything. Even if we know that they are irrelevant, we can't do anything about it. So now, how can we do anything, or how can we do something to control these coefficients so that the irrelevant attributes do not add to complexity and overfitting of the given model? So to put a cap on it, this term was added. Okay.
Okay. So T
This
is
is,
also part of the equation, I guess. T.
T is not, you can think of it as a part of the equation. Sometimes this expression is also written as this minus T,
Hmm.
but anyway, this is a constant, so you can just ignore this also. So I'm just putting it directly. So the summation has a constraint that it has to be always less than T. I'm putting this just underneath to show this thing. Okay. So
Hmm.
this value is always less than T, this value. Now, when this value is less than T, it can come to mind definitely, like you are thinking, what is the big deal? We are only putting a cap on the coefficients, so that their magnitudes are less than or equal to something, right? You
Yeah,
saw that,
and because anyways, if this lesser than T, if we are applying anyways, it is impacting the left side, which is xi
yeah,
into pj. So
that's
why to keep?
exactly what.
Yeah, yeah.
No, no. So the thing is that when we put this constraint on it,
Mm-hmm.
then these coefficients, which are part of this only, na, they
Mm-hmm.
are also getting, so these are the same coefficients.
Right.
So because these are getting reduced, this whole term is also getting reduced.
Okay.
And
So it's
therefore
it's
the
to better
error is
represent.
getting reduced. Yeah.
Okay.
So we want to reduce the error, uh, or we want to actually, what should I say, not reduce exactly, but we want to reduce, and yet we want to make our model less complex. To
Mm.
make it less complex, we want to ignore those attributes which are useless, or we want to downgrade them. So this is what we are doing. By doing this, the values, as you can see here, see, originally the values were, the solution was here, but
Mm-hmm.
the constraint that we have put is forcing it to become, to lie in this region somewhere.
Mm-hmm.
So in this region, there could be concentric diamonds, and it could lie on any of these vertex,
Mm-hmm.
depending upon what the constraint is. Obviously, this is the worst case where constraint means it is zero, means there are no predictors that are allowed, because this beta will be zero, and so everything will get removed, and what we'll get is only alpha. I already showed you that equation.
Mm-hmm.
So, but we have putting it to some particular value. So the actual value was here. We now are restricting it to here. And then we want to bring the solution in such a way that the mean square error, this one, satisfies this constraint. And so this is the intersection of the point.
And
And
ma'am,
it's,
ma'am,
yeah.
I understand. So while removing, let's say making somebody some coefficient zero, do we also, I mean, model might automatically do it, but do we also give priority to some of them that these should not be removed? I don't know. It's a silly
In the
question.
basics form, I haven't yet come across any priority,
Okay.
because it will automatically, it's an optimization problem, and it will do that.
Okay.
Okay, Vipul, you have a question?
Yeah, ma'am. Just two things. One is if we increase the value of t from 4 to 8, so
Mm-hmm.
will the sweet spot, you said na sweet spot is mostly
Yes.
intersection
The,
between the rhombus and the eclipse, right? So that will also
yes.
share, that will also change. But will that have
Yes.
an effect on our calculation, and will that have effect on our model as well?
Yeah, it will definitely impact our model. let's say that if you had a constraint which was this big, I should not, I'll have to readjust this. Let's say there's a constraint like this. This was a constraint. Or in other words, we are allowing much higher values of beta. Then the MSE, that will come here will be this, somewhere here, because there are infinite number of ellipses like this, right? So this will be the MSE equation that will fit. So this will be the impact. So if we choose the constraint to be having a lower value, what we will get here, when this is lower, right? So the coefficients will be much smaller and this will get impacted. Similarly, if the summation is higher, the coefficients are allowed to have higher values. Therefore, the MSE here will be this. So if this is the MSE value with the ordinary least square, so in the case where the constraint is larger, this reduction will be much less. You can see here the difference between this and this is less. Whereas in the previous case, when the constraint was smaller, the reduction in the distance between this and this is larger. So it purely depends how much we want to, reduce, or how, what kind of constraint we want to put. Accordingly, this value of t will be decided, which is the threshold or the constraint.
Thanks for
And
explaining that.
accordingly, MSC will get affected. Yes, please. What are you saying?
Yeah, thanks for explaining the same stuff. Just wanted to another question is,
Mm-hmm.
will that the spot will only lie on the axis then, or beta two or beta one, because
It will
there's
always lie on the vertex.
what? Okay,
Yes.
okay,
And I told you the reason why, because any other point, so this distance is always going to be the maximum, right? In a diamond or a trapezoid, this distance is always maximum. Any other distance will be less than that only, because this is going to be going towards perpendicular. So this is the largest distance. And therefore, when we have the largest distance, therefore the minimization will be maximum. That's what we want.
thank you, thank you.
Yeah. Any other questions, anyone? Okay. So now, a second. Just looking at my notes. Oh. So I already told you all this stuff. And so you can see that in this L1 diamond shaped figure, the origin will show, I already told you, the point where all the coefficients will have zero weights. And in this particular case, when all the weights will be zero, then in this expression, for example, if this was the expression, this is just an example. If all these were zero, then these will get removed. And what you will be left is only this. So we don't want actually so much restrictive also. Okay. So now, okay, so before we go here, now suppose we want to minimize, we want to find a, so far what we had done was we have tried to put a cap on beta, summation of beta. And when we try to put a cap on summation of beta, then what happens is that the whole of the expression goes lower, right? We had this expression, which is the loss. This was the expression that we had earlier, which we tried to minimize by putting a cap on here. But what if we try to minimize this whole expression? If we try to minimize this whole expression, then it will go like this. It is called argument minimum, means minimum of this complete this thing. Yi minus beta naught minus xij bj whole square plus beta j. This is going to be the expression here. Here we are trying to minimize not just this, we are also trying to minimize this. In the previous case, we tried to put a cap only on this, and when we try to put a cap on this also got impacted, right? So to do that, we will use, so far what we had done was just put a hard, hard boundary or a hard constraint on the value of this constraint. Now we'll talk about a soft solution. And what is a soft solution? A soft solution is not just putting a constraint, but uh, if we have a further control on it, then how is it going to work? So for example, if we have a soft solution, this soft solution will look like which is the most important thing now. So now we have put an extra term. This is lambda. And this is what the lasso is all about. So far I talked about a hard constraint where we decide a value, threshold value, and that threshold value is just fixed and we can't do anything about it. But what if we want to fine tune it in such a way that we could adjust this value also? So we should have the capability to adjust this value further, right? And therefore we have this lambda added here. This lambda out here helps us to adjust the constraint on this also. So suppose we want to weaken this further, we could do it, or we want to strengthen this summation, then we could accordingly change lambda. So this means that if we have lambda tending to infinity, then summation of beta will be tending to 0. Why? Because if lambda tends to infinity, then what will happen is this whole expression, this is the loss, total loss. So this whole expression, if this tends to infinity, then this whole expression will tend to infinity. But we don't want that. We want that to be minimum. So if this tends to infinity, then this has to tend to 0. Or if summation of beta is so high that this one tends to infinity, then lambda has to tend to 0. So this works in a inverse fashion. And this lambda provides us a soft control over this hard constraint value that we can further upgrade or downgrade the coefficients based on the choice of this lambda. Okay. So if we talk about it in brief, and if we talk about L1 regularization or lasso, then what are we doing? We are having this overall loss and we are doing this. This is what we are doing in lasso. We are adding a penalty, which is lambda times, and this lambda is again a parameter. And you can just look at the lasso part right now. So I already told you this is the actual value, okay? And then you have the and then you have the After the actual minimum, you have the actual error gradient, which are these gradients of these curves. So, and this is the minimization after regularization. So this is the L1 norm penalty. So this is the diamond shape penalty constraint. This is the point where coefficients will be 0. And this is the point where the error will be minimum. The minimum error is the error which is the overfitted model has, which is obtained by simple, applying simple linear regression. And what we want to do, we want to bring these two close to each other, optimally close to each other. And we can do this with the help of this particular, by having the intersection of the two, and the best intersection will be at the vertex only. Okay. So if you look at it in a 2D fashion, what we will have is, suppose we have this as our the minimum loss, and we want to, when we have this minimum loss and we want to find out, or we want to minimize the error, then any of these situations could be there where the vertex of the diamond will be helping us to solve our problem, and it will be the one that will be always helping us to minimize the sum of squared error. Okay. And these concentric lines, as I already showed you, are the sum of squared error or mean square error or the loss function. So I've already explained you that the red lines show the loss, and the blue region represents the constraint. And we always want to have a solution between the two, that is the loss intersecting with the constraint. So this is what is already written here. This is another diagrammatic representation. So you can see here that if we look at this particular value of the loss, if we look at this point, and if you look at the vertex, then you can see here that the mean square error, which follows concentric fashion, the loss here, the difference between this minimum value and this value will be highest, because you can see mean square error here is, this one is passing, and here a higher mean square error will always pass accordingly. And therefore we want to choose the lowest error, and so we will choose the vertex. So I think I've pretty much told you, this is just a 3D representation. I found it interesting, so I put it here. In this case, there are 3 coefficients, for example, and the square will actually be replaced by this kind of a octahedron, where we have got 3 coefficients, and we want the constraint to work on these 3. Okay. So mostly the explanation I have done. Only thing is that, okay, any questions so far, anyone, on whatever we have done? So then, as we saw that this parameter T actually controls the amount of shrinkage that we are applying to coefficients. Shrinkage means we are making them to be smaller or equal to the summation of all of these coefficients to be smaller or equal to the constraint that we have put on it. If the value of the summation of all the coefficients is larger than the constraint we put, then no shrinkage has been applied. Okay, and in that particular case, the solution of the lasso will become same as the solution of the simple least square method or the regression, simple regression. So when the value of the summation becomes less than the threshold that we apply, only then the solution becomes the actual lasso solution. Okay. And when the value of T starts decreasing, that is the threshold or the constraint that we put starts decreasing, the coefficients also start shrinking to fit that constraint. And in that process, some of the coefficients will become 0. And these are the coefficients that tend to those particular predictors that were probably not important for this this particular prediction, and therefore the lasso process, the lasso regression is going to reduce them to 0. So this is the most important property of a lasso regression or lasso or L1 regularization, that some of the predictors which are irrelevant for that particular prediction will be put to 0. Or in other words, they will be removed from the prediction model, or in other words, the model will become simpler with fewer number of non-zero coefficients, and therefore it will not overfit, and therefore we avoid the risk of the model getting overfitted. So I've explained everything, the hard constraint also. The only thing is that here what I'm showing you this figure in 3D. So this is the orange one, shows the penalty. Okay, this penalty out here, and this one actually shows the loss function, and the intersection between the two is going to give us the solution. So more or less I have explained to you this particular function, which is the argument minimum. Then I've introduced the term lambda already. I told you that lambda helps us to fine tune, and this is what the lasso is all about. And the relationship between lambda and the coefficients is always inverse. So when lambda increases, the coefficients will decrease, and when coefficients increase, lambda will decrease. Okay. And therefore, different values of lambda is going to actually impact the model. And how it is going to impact is that since lambda is going to represent the amount of regularization that is being done, and it's also a hyperparameter that is chosen. So if we increase the value, beta will decrease and it will look something like this. So let's say this is the original graph when lambda is equal to 0. So when lambda is 0, then this term becomes 0, and what we are having is just this one. And this is the basic equation. As lambda increases, we can see that the coefficients keep on decreasing. If this is beta 1 and this is beta 2, then the value of the coefficients will keep on decreasing like this. And at infinity, what will happen is that the coefficients will actually become 0. So this will become a constant value, and it is only having the value of the intercept C. Or you can say this is only alpha here. Because in this particular case, both beta 1 and beta 2, if this is an equation of this form, which I have been writing again and again, alpha plus beta 1 times x1 plus beta 2 times x2. So in this particular case, when lambda is tends to infinity, all these will tend to 0. So this will get removed, this will get removed, and this is a constant value alpha. So this is what will be the impact. Now coming to the important part of this is application. So there are, as already discussed, the most important application of lasso regression or L1 regularization is feature selection, because in this process, some of the irrelevant attributes will be removed because the corresponding coefficients will be made to 0. Remember that the minimization will be happening only at the intersection between the ellipsis and the diamond, and that will happen only at the vertex. And at the vertex, some of the coefficients will be 0. If it is a two-dimensional plane, we have only beta 1, beta 2. So 1 out of beta 1 or beta 2 is going to be 0. So the corresponding predictor, if beta 1 is 0, then x1 will be removed. If beta 2 is 0, then x2 will be removed, like that. So irrelevant features will be removed, and by removing this, the sum of squared errors or residual sum of squares will be minimized. Then the next application is sparsity. So it is ensuring sparsity by having more, uh, by having coefficients assigned to 0. So therefore, lesser features are included in the model, and the model is said to be a sparse model. A sparse model is one in which not all features are used, sparse number of features or few features are used. And such a model will be it will be computationally faster and more efficient, and it will also be more interpretable because the number of uh, uh, predictors will be lesser than overly overfitted model. Collinearity will also be discouraged by using lasso regression. And in this particular case, if there are features that are correlated, automatically some of these features will be retained while the others will be downgraded to zero. Because the model works like that only. So collinear features will be removed and redundancy will be removed, and the model will become less overfitted and more generic. And model simplification, obviously, we are achieving model simplification because features are getting removed and model is becoming more generic and it is becoming simpler. So these are some of the applications. Now that I have completed L1 regression, if there are any questions, you may ask me. Then I'll begin with L2 regularization.
Yeah, madam, this is Shreyapan, madam.
Yes.
Yeah, madam, what we understand that we want to fine-tune the model using this lasso so that it should not go underfitting as well overfitting. We should make some generalized way that the model can be
Only one correction, only overfitting we are seeing here, not underfitting. Okay.
overfitting. Madam.
Yeah.
So, madam, this is a linear regression. It's just a set of data where independent and dependent variables. We want to know what the relations and where we can select the features, which are the selection, which are the parameters for we selected. Now,
Yes.
when this in a case when really in the world, what I see that most of the data are this, location based or geographically weighted. So where can we use Med? Because this is only for OLS we are talking.
So this is any data that you are expecting uh, that might face overfitting. There you can use this kind of a regularization. For example, as I told you, let's say we want to predict sales of an item. Okay.
Okay.
So the
Okay.
sales of an item may have a region as a particular attribute. So latitude, longitude, or some information about the region. Then it might have the items that are on sale. It might have some other things, but if it has the name of the store also, like that. So the name of the store or maybe some particular store ID is there. So store ID is not a predictor, but it's there in the data. However, because let's assume if this is given as an input to a linear regression model, it's also going to incorporate store ID also because that was given as an input to the model. So the model doesn't have any discriminative power per se to identify which one to use and which one not to use. So to equip the model with such a capability, we have this lasso regression or lasso or L1 regularization, where we have a penalty or a constraint term. So this constraint term will help us to uh, keep a cap on the value of the coefficients. And when we keep a cap on the value of the coefficients, automatically the entire expression gets impacted. And additionally, we also introduced a term lambda, which not only just helps to put a cap on it, but it further helps to fine tune the summation. So if we want, let's say that the constraint is so small that, so I think I'll request Govind not to draw on the screen. Please stop drawing because it gets saved otherwise. So Govind, are you there? Can you please stop doing all this? I don't know what is the purpose. Anyhow, so like this, we actually, we So we are equipping, making the model more enhanced so that it can select the features by this process. Those features which are either they are correlated to each other or they are irrelevant, they get removed automatically.
Okay. Thank you.
Yeah.
Thank you, ma'am.
Yeah. That's... Any other questions? Okay. So I thought that I will,
Ma'am, I have one question here.
yes, yes, go
Just
ahead.
can you explain on the collinearity part how actually it identifies this one?
So the thing is that explicitly how it will identify, because the lasso is designed in such a way that it looks at the coefficients and try to find out that vertex, right, where the mean square error satisfies the constraint. So in this process, it will automatically identify those particular features which behave similarly, which have a similar impact on the on the expression of the error. And therefore, what it will do is that it will choose some of them, the minimal set it will retain, others it will equate to 0. But I haven't shown you the math for that already because I felt that this is also becoming heavy on math.
Yeah, I got it. Okay, okay, ma'am. That's fine. Yeah.
So,
And ma'am, just one thing.
yeah,
So
yeah, yeah.
that ellipsis that is forming is because when it's a silly doubt. So the ellipse that is forming is the error function because it's a square, so it's of a shape of the square of multiple coefficients. That's why it's ellipse shape. And moment we are increasing the error, we are trying
Mhm.
to reach nearer to this diamond edge so that we balance between how much we increase. Is that what is happening?
Yes, exactly. So these ellipsoids actually,
Mm-hmm.
if you plot the mean square error
Mm-hmm.
or the sum of squared error, you will get something like this for
Okay.
different combinations of beta. So for
Okay.
certain set of combination, it will be like this, like this, like that. It
Mm-hmm.
will go on and on
Okay.
like that. And so this is the minimum value, but this is the overfitted model. And
Mm-hmm.
that's why it's having the minimum error. We want the model to be a little generic, so we want to increase the error on it. So
Mm-hmm.
we have to decide how much error to increase. At the
Mm-hmm.
same time, to increase the error, it should also not happen that the error is so increased that a model becomes underfitted, which is the case where this is very far. Let's say if this was here, then it will take a while or it will make the model so very generic like this
Mm-hmm.
that it that will this will still lead to underfitting only. However, we are assuming right now that our model is overfitted and we want to increase the error in such a way that some generalization gets added, but we want to also limit the generalization, right? We cannot go on till go on generalizing it and on and on till it becomes underfitted. So we are putting a constraint. So the point where this generalization meets this constraint is our solution.
Okay. Okay.
Okay, Meghna, do you have a question?
Yes, ma'am. Now, from a practical implementation standpoint, where does this fits in? Like, is it by like whatever linear regression we are implementing, then the observation of the overfitting errors, etc. Then we come back and strategize to implement Lasso, or is it a best technique or standard technique we do at the beginning? So how do we determine this?
So if you feel that you have a risk of overfitting, then you use lasso and ridge regression. Otherwise, it's not necessary to use it always. It's primarily for regularization, and regularization means cases where you have overfitting, where you have identified overfitting in the model. If you remember in the hands-on also, I've shown you several cases where overfitting is happening. So one way is to try to just see which are the best parameters to use to avoid overfitting. Other is intentionally change the model or modify the model in such a way that overfitting can be avoided. So these are the ways to do that, lasso and ridge.
Okay.
Yeah. So you don't start with Lasso and Rich right in the beginning. But if you find that your model is overfitted with the help of the training, test error, and all that kind of stuff, then you can use this regularization methods and reduce that. So I think I'm seeing again and again this thing happening, writing happening on screen.
I think this is Govind, ma'am. Is it correct?
Yes, yes. Earlier also it was Govind
Yeah. So
only.
Govind has left the course. I'm not sure why he's still having the access.
Madam, he
Simran.
may be removed, madam.
It's two
It is
persons,
disturbing.
right? Yeah, Govind. We need to make sure that it is the same Govind or it is a different Govind. Govind, can you come up and please speak here? Either maybe your kids is doing something
It's
or
disturbing our teaching method.
Yeah, he has left again. So looks like it is purposeful.
yeah,
That is to
Govind.
block, madam. That
No, he's the
that access
same
to block.
Govind. I'm pretty sure he's the same Govind and he is doing it on purpose.
Yeah.
Then what's the Simran or the Futurance is
Simran,
doing?
could you please check?
Means I mean
Exactly.
people who have left the course and they have taken back their money and we are spending these monies for
Yeah, let me check. He's not in the
So
call now. If he joins
But
again, I
that
will remove.
check means your security is breaching. I mean, the course security is breaching. We are paying, we are here, and the people are taking benefit of it.
Simran,
Concern is that
I suggest that please, I think you please make sure that the link is not shared and LMS access is removed
Block.
for those who have left the course so
no,
that
ma'am,
they don't get a link.
anybody. I think the if someone share the URL to someone, I think he could join. It is something like this in the Zoom.
Okay. So
Yeah,
I think
ma'am.
at
So
the
even if the LMS access is not there, I mean the Zoom URL could still be accessed by people who have even
Mm.
not, enrolled in the course. So it's directly
Yeah.
accessible.
Just one point, ma'am. How Ashish is joining your PhD student? Do you invite?
No, yeah, I invite him.
Okay. Is there any password or something on which basis he's joining? You just share the link and he can join.
No, yeah, it's just simple sharing of the link.
Yeah, that's why other people can join from there and in the
Yes,
same
yes.
way.
So
So this
I
is the great,
agree.
this is the good
Yeah,
example that the security is breaching here.
yeah.
One more thing, there are email also going across. So I think we need to remove him from the email ID list as well. Simran, just
Yeah.
take a note of this as well.
Yes.
Even a firewall can be given on that.
So I think I don't know if that's possible, Simran, that the initial start when the registration happens, if there's an authentication there, then somebody who's not registered by an email ID will not be able to enter. You can just give
We
some
can
thought on
do
it.
that.
Yeah,
We
please
can
do
do
it.
that, but in that case,
So,
you will have to log in and sign into your Zoom.
Yeah, that's
Yeah,
okay.
but everybody is able to
but
join.
Simran, those people who have left the course, are they still have access to the LMS? I mean, their access has not been removed.
I don't think as yet it is.
Yeah,
Yes,
otherwise, whenever we join, it always asks for the register email ID. So probably they are still having that in the region. They are able
No,
to.
no. The thing is, anyone can register and join
Oh,
now, but if we make it, if we authenticate it, you'll have to sign in.
okay.
So probably some way of authentication should be there. And without signing in also it is possible, I believe, because for some other courses I've seen also that the people who are not registered are not able to join. So maybe you can work on it, Simran. This should not happen. That
and
the class gets
why sorry is being written here on the screen? Means really means scaring it is. Why is doing like this?
Yeah,
not sure.
Prashant, I think he already intentionally did it, right? Let it be like discussing on that part. It will consume our time itself only. Let's move on.
Right.
Next time
No,
when
but
he joins, like Simran can revoke or like she can take some action.
Yes, it is intentionally he did. Yes, you are correct.
actually now I cannot remove this. The person who writes only can remove. So what I'll do is I'll do a stop share and then reshare. But then all the annotations will be gone. So I thought that I'll share the annotations with all of you. Unfortunately, now I'll have to remove them. Okay. So just give me a second. I'll just do a stop share and then do a reshare. I think I have done a stop share.
Yeah, ma'am.
Oh. Oh, now I think it's okay. I was able to. So we are done with this one, L1. And I told you about all these things. Okay. Now let's talk about L2. So the only difference between L1 and L2 is this one is a square here. So the rest of all the stuff is just the same, with the single difference that lambda times, instead of the absolute summation, we have now the square of values. Now what impact this is going to have, that is important. So now in this particular case, in the previous case in Lasso, you saw that the intersection of the two was always a vertex. In this particular case, what will happen is that the coefficients will be shrunk, but they will never become zero. And the reason is that in this particular case, we are having a circle. So let's say that yeah, just a second. So suppose we have again the same set of coefficients that I showed you. We have alpha plus beta 1 times x1 plus beta 2 times x2, and our constraint, the value of t is suppose should be less than or equal to 8. And now if we try to plot this particular function, where we are having what? We are having the beta squares out here. Okay. So if this is the case, then so in this particular case, let's say if t is less than or equal to 8, or in other words, beta 1 square plus beta 2 square has to be less than or equal to 8. So one possibility could be beta 1 equal to beta 2 equal to 2. So this is that particular value. The other possibility could be beta 1 equal to 1 and beta 2 equal to under root of 7, which is 2.6. So if beta 1, if this is beta 1 and this is beta 2, then beta 1 could be 1 and this could be 2.6 or something like this. So if you plot all these points, what you will get is a circle like this with a maximum value here, like this. So it is 2.6 here and 2.6 here. So in this particular case, instead of the rhombus, we are getting a circle. So the constraint is satisfying a circle. Okay, this is the difference. And now this remains the same. So this is the minimum value of the error. And as the coefficient combinations are changing, the error is increasing. So this minimum value of error indicates a overfitted model. And we want to increase the error so that the model becomes more and a little more generic. So what will happen, we'll go on increasing it till the constraint gets satisfied. And this constraint will get satisfied here. And because this is a circle and not a diamond, therefore the satisfaction of this constraint and the MSE will always happen on a point which is other than, there will be no point which will be on, because there are no vertices, so there's not going to be a vertex kind of a solution here, and the solution will always be on this, in this fashion. So this is how the lasso works. So the difference, and because there is no vertex per se, therefore none of the coefficients will become 0 here. So this is a major difference between lasso and ridge. In case of lasso, because there were vertices, one of the coefficients became 0. If you look at this figure out here, yes, this one. So in this particular case, what is happening is when we are trying to increase this mean square error, what is happening is that here this error is getting increased to whatever the optimal limit is. Whereas here the error is even more, because this vertex is protruding, therefore it could actually touch a lower MSE line. Whereas if this was a circle like this, then it won't be having any vertex, and therefore this point will be somewhere here only. There's no concept of a vertex here, and hence that's not going to be like this, and or in other words, none of the coefficients will be assigned to 0 value. So L2 or ridge regularization always tries to downgrade the coefficients because it has got square, right? So what it will do is in this equation out here, so this is the equation, and the constraint on is this constraint can also be indicated by this is the loss and this is the constraint. Earlier also I said that minus s or minus t, if we call this as the value, this could be taken like this, or because t is a constant, we can simply write this equation like this, right? And this is what we want to minimize. And by doing this, but because beta square can, because these are squares, and there is no concept of a vertex here. It is a concept of a circle or a sphere or whatever the dimensions are. Therefore, uh, none of the coefficients are going to be 0, but they will be shrinking. They will be downgraded in such a fashion that the overall error gets reduced. When these shrink, then what will happen is that here the values will also decrease, and therefore the overall error will decrease. And a further fine tuning can be done with the help of lambda. If lambda is increased, then the strength of the coefficients can be increased. If lambda is decreased, then the accordingly it can be used to fine tune. Right, but in any case, none of the betas will be 0, and therefore the regularization does not help in feature selection. It just minimizes the coefficients by putting a constraint. Now, because this is a square value, therefore, in this particular case, because it's a square value, this will have a large value. When this will have a large value, then accordingly so this means that because we need to satisfy a constraint and square is large, therefore the individual value of beta j has to be less, so that its square is less, and within the constraint the coefficients can be accommodated. Or in other words, this, because this value is the bj, individual bj will need to be small so that the square becomes small, and all the bj gets accommodated within the constraint, because none can be equated to 0. And therefore here also the coefficients will be reduced, and the model will be having all the predictors in it, but they will have less value of the coefficient, so their weights will be small. So the model will be kind of smooth and stable model, and it will not have too high, too low kind of coefficients. So this is special, okay. This is already shown here. So now the advantages is that in case of Lasso, we could actually remove some of the coefficients and thereby we remove the features. But suppose if we don't want any of the features to be removed, if we know that we want to retain all the features, then it's better to use L2 regularization or ridge regularization, in which features are going to be maintained. However, their weights will be downgraded or minimized so that the error gets minimized. Also, because the coefficients are small, because the error, the penalty term will contain the square of the coefficients, and the square of the coefficient is anyway larger than the coefficient itself. So the coefficients have to be made small so that the squares are also small and all of them get accommodated in the given constraint. Therefore, the coefficients will tend to decrease and the model will have a less variance. It will be a smooth model having very less fluctuations, and the influence of the predictors on the prediction will also be less. Each and every predictor will in turn have a less impact on the prediction. More or less every predictor will have some impact, but it's not that one particular predictor will have a high impact. This was possible in Lasso, where some of the features could be made 0, whereas others could dominate. In this case, none of the features will dominate. All of them will have some contribution towards the prediction. This is the purpose, and therefore it promotes feature maintenance and stability in the model. Then we have how it deals with collinearity is that implicitly, because of the way it works, it allows the all the features which are correlated to have same amount of influence on the model. So their coefficients become, because all the coefficients are quite less, so what happens is that the features which are also correlated have minimal impact on the model, because each and every feature has almost similar impact and very uh, they are downgraded to some extent and the model is so smooth. Therefore, collinearity will be discouraged in this also. So this is about L2 regularization. Pretty much everything is the same, only in this case here the constraint is circular. That's the only difference here. More or less all the other constraints remain the same. So yes, Rajat, what question do you have?
Ma'am, I have a question for lasso regularization. So the axis of this ellipse, which is formed by combinations of beta 1 and beta 2, will that axis, direction of that axis not matter? Why is that direction always intersecting at the corner of the rhombus?
I showed you. Yeah. The tilt you are talking about, right? The tilt of that. It doesn't really matter what tilt it will have. See, here I have shown you that if it was a tilt, if it was a point here, then also it would have ellipsoids, right? And in that case also, I haven't drawn properly though. So it actually doesn't matter where it is, and I have a diagram also. See, these are the different situations. It doesn't really matter which direction it is. It's always going to find out this spot only, because any other line is going to have a higher MSE value, right? This circle, the larger it gets, the more it is. We want to, definitely we want to increase the error from this overfitted model, but we don't just want to go on increasing it. We want to keep it at some constraint. We want to, stop it somewhere. So this is a point where we stop. So it is always going to be at the vertex only. And if we take any other point in between, it will be larger. You can see here, this vertex is this line of MSE. But if we take any other point, these are all higher. Do you get what I'm saying?
Yes, ma'am. Thank you.
Yeah. Any other questions, anyone?
Ma'am, I wanted to clarify one understanding.
Mhm.
For the linear regression model, if the coefficient for one attribute is high, does that
Mhm.
mean it means that the attribute is contributing less to the model as a concept?
If the coefficient is high, it means it is contributing more. Suppose you have this equation, y is equal to alpha plus beta naught x1 plus beta 1 x beta 2 x2. Okay. So these are the two predictors, x1 and x2, and these are the two coefficients. If the value of this coefficient is, let's say, 10, then this value x1 predictor will get weighted by 10. So a value of 10 here becomes 100. Whereas if this is, let's say, 0.1, then this x2 is getting downgraded by 1 by 10th value, isn't it?
Okay.
So whatever is the weight, accordingly it will impact that predictor.
Okay. No, I was asking, ma'am, the x1 here as a in the model, x1 as an attribute,
Hmm.
the contribution of x1 is less than x2 because the coefficient is more for x1. Is that a valid statement?
Not necessary. The thing is that if the model is giving more weight here, is finding out more weight, it seems that x1 is a dominant one as compared to x2. Accordingly, more weights are being given to it.
Okay. Okay. Thanks, ma'am.
Yeah. Any other questions, anyone? So in the one thing I thought that because all these maths are quite important and also interesting, so I included it. But you all can suggest if you feel that it's a little heavy or dry. In future, I may not
No,
include.
I prefer having them. This will help those people who are interested in understanding them, because
It's okay, madam.
those who don't want can ignore it. Maybe you can suggest that maybe those who don't want can ignore it, but it helps us because I cannot cross question on internet while reading all these things. But when you are there in the call, I cross question so many things, right? So that helps. Yeah.
Yeah,
Okay.
concepts clear. It's getting concepts are clear, madam.
Okay.
Agreed to having mathematics.
I couldn't understand what was the last comment.
Agreed to having mathematics.
Okay. Okay. Okay, I could see some hands raised. Are there any questions, anyone? Okay. So then I think before we wrap up for today, we had discussed that we will share a file which will contain the information about all of you, which will help you to form groups. So Simran, I request you to share it here on the chat so that people can see. You can please open it. I'll do a stop share and you can open it also, Simran. So students can get a quick view and then they can also download and just talk to each other and try to form groups.
Yeah, currently only 74 people have filled in.
Okay, can you please just show it once? If you can enlarge slightly. Okay. So I think this is the information that we got. Since I think Simran will be sharing it on chat. So those who are interested can download and start trying to connect with people whom you think are going to be similar. And I request all of you to please fill this. It's going to help you all only. It's not for us, it's for you all. So please fill it, those who haven't filled, so that you can accommodate yourself in groups. Now, remember, a group that you form will be much better than what will be formed by us. So, okay.
How to download it? Where is the link?
I think it's on the chat.
Okay.
Okay, then I think so. Once we have this information and all of you try to form groups of size 7, shall we discuss about the groups? How many are formed?
Ma'am, one quick thing, like whoever
Yeah.
is not added, it is a auto save, right? I think since like I missed it, I haven't added. So we can still
Yeah.
refresh and take the.
I have still sent the link on the chat. You can fill it up soon.
Okay.
Simran, I
It's
think you
not
need to approve the
approve the
access.
request.
I'll do that.
So I request all of you to try to accommodate yourself in groups. And Simran, I request you to share a form in which people can fill up their names like group wise. So those people or those learners who have formed groups, they can get accommodated. Okay. So yeah. And then whosoever is left, we'll see how best we can accommodate. So I think with this, we are done for today. And one thing I want to say is that for tomorrow, though I had written earlier that we'll be doing hands-on on clustering, but tomorrow I'll try to first complete hands-on on this regularization. If it gets over, then we'll do the clustering part. Otherwise, we'll concentrate on this first and then do the clustering in the next week. Okay, so the schedule that I provided to you gets modified slightly because of this class extra. So I did not plan earlier to take one full lecture on it. At that time, I thought that I'll just tell you about the formula and all. But later I felt that it will be nice because this is a good question which is asked many times in interviews and many other places, and those who are interested to know it conceptually, like I like it to know conceptually, maybe. So that's why I included. Okay. So please
Thank you, ma'am.
consider that. Yeah. Thank you. Thank you all. Have a great
Thank you,
evening.
ma'am. Thank you, ma'am.
Bye-bye.
Thank you. Good night.
Thank you. Good night. Bye-bye.
Thank you, ma'am.
Thank you.